Hey all, it's Andrew Couch here, and this Tidy Tuesday video, we're not going to be looking at this week's dataset. Instead, we're going to continue to work on the Tidymodels packages and focus on classification models, specifically on the model metrics. So when we think of classification model metrics, we always think of like accuracy, but the accuracy is basically composed of the confusion matrix, which the confusion matrix has four main values: true positives, false negatives, and true negatives. You may also have heard of like sensitivity, specificity, the true positive rate, false positive rate, precision, recall. All of these values or all these metrics are basically composed off of the confusion matrix. So that's what we're going to be focusing on. And what's cool about the Tidymodels package is that there's a package called the Yardstick package. And this will basically be the main package for basically calculating and charting out these metrics. So let's open up a R Markdown file. R Markdown. I'll call this Tidy Tuesday classification metrics. Okay. I'm going to delete this garbage. I'm going to open up the Tidyverse. Was it Tidymodels? And we're actually going to be using the same data set from last week's video, which is the customer churn data set. I would also like to say that you should subscribe to my channel because every week I make a video trying to teach about data science. And I've definitely focused a lot of my videos on predictive modeling using Tidymodels. So if you want to get better at Tidymodels or just learn about machine learning, hit the subscribe button and I'll see you guys next week. So you guys heard my elevator pitch, and let's actually start analyzing this data set and creating some models. So when we're looking at this data set, the first thing that we should really be doing is counting the class that we're trying to predict. In this case, this is a customer churn data set, so we're trying to predict whether a customer will stop our service or not. In this case, since we counted the things that we're trying to predict, we can see that there's a difference in the no's and the yeses, where there are much more customers who will stick with our service than customers who will stop our service. Additionally, we would want to consider the yes as the positive class. So we can see that there's a class imbalance in the positive class. So we can say this: evaluate class imbalance. We can see that the yes is imbalanced, and that'll actually affect of how we evaluate our model. So if we also look at our levels, so if we do churn and then levels, oops, oh, you can't pipe that. Oops. If we look at our levels, whoa, what df level? Oh, I know why. As dot factor. So if we convert these things to a factor, we can see that the factored levels are in a different order. With the Tidymodels, they actually view the positive class as the first level in a factor. So we're gonna have to keep that in mind. So if we say this, we'll say need to change levels for churn. Okay, so now let's actually clean the data. If we do a summary, we can see that most of them are characters. We're also missing some NAs. So what I'm going to do first is I'm going to drop the NAs. And I'm going to convert all of them to a factor. So all these features will be factors. So as dot factor. And now I'm going to actually fine tune and convert the few features into a numeric feature. So in this case, we're going to say tenure is a numerical feature. Monthly charges is a numerical feature or continuous feature. And let's see here, total charges is our numerical feature. So as dot numeric total charges. Cool. So we did that, and that will be our data cleaning. It's pretty fast. And we're also not going to do any crazy feature engineering either, because I want to focus this video mostly on the metrics and not the actual modeling process. Oops. If we also look at our, so now we should also change the levels. So if we see the levels, df, churn, we still have it no yes. What we can do is actually re-level the data. So change levels. So if we do df mutate churn is equal to factor reverse churn. And then we do levels df churn. We can see that we just swapped the order. So that way we can have the yes as a positive class. Great. So now let's actually create our train, test, and validation sets. I'm going to set the seed for reproductive, so you can replicate it. I can never say that word. It's a tongue twister. So now I'm going to create the, the data splits. So data split, initial split, a df prop equals 0.8. We'll say strata is equal to churn, so that we have an equal classes for each split. Oops. And then we'll say train data, training, test data, testing data split. And then I'll say k folds, v fold, cv, give it our train data, and then we'll call that day. So we created that. This will act as our validation set for our tuning of the model. Okay, so now we're going to actually do the pre-processing. We're just going to do a basic recipe. So we'll say recipe churn data equals train, data equals train data step remove, because we want to remove the actual customer ID. So we'll just remove that. We'll basically normalize all of the nominal variables, or all the numeric variables. I just did step range because then we'll know that it just converts it to in a range of 0 and 1. You can obviously do step normalize or step normalize and boxcox. You can also do step center, step scale. But I figured step range was just kind of like a thing to do. Definitely up to the modeler's discretion. We're also going to do step dummy and say all nominal, but we don't want to do the outcome, which is our churn. I'm also going to say one hot is equal to true, because I don't want to have any degrees of freedom. I kind of just want to have the each feature being representative. Okay, so I'll say model rec. If we do model rec prep and then juice, we can see it actually being applied to the training set, and we can see that we have our one hot encoded variables. If we do the summary, we can see that if we look at the min and maxes, that all of them are between 0 and 1. So it's doing exactly what we want it to do. Okay, so now we're actually be looking at the metrics. So what we're gonna do is we're gonna say like classification class. We'll just call them C metrics. And what we can do is when you're doing a classification model in Tidymodels, they'll always give you the accuracy. But in this case, what we're going to do is we're going to just give it a whole set of metrics. First, we're just going to give it accuracy. We also want sense and sensitivity and specificity. I'm also going to include AOC and ROC. And then I'm also going to use the mean log loss. So let's go back to this and we'll see accuracy. Accuracy is just the total true positives plus the total true negatives divided by a total amount of observations. Okay. Sensitivity is just the true positive rate divided by the true positive plus false negatives. So out of all the positive classes, how many were correctly predicted? And then and then specificity is just out of all the negative classes, how many of the negative classes were correctly predicted? Okay, which is pretty useful just on like information standpoint. So if you're saying like, okay, we want to figure out how many sick people out of the population, how many sick people were correctly identified, it's pretty useful. But there's also other metrics, specifically that the true positive rate and the false positive rate. So a lot of these metrics are kind of like they measure slightly different things, but they're definitely linked to each other, which can cause some confusion. But we're not gonna have to worry about that yet. We'll get into that after we start making our models. I'm also doing a model control where I'll do we'll do a control grid, and I'll just save the predictions. So that way we can add any other metric we want using the Yardstick package. So for the actual modeling, I'm just gonna create one model, and this model will be a KNN model. I'll say nearest neighbors equals tune, set mode, classification, set engine, KKNN. And I'll say KNN grid. So I'm going to create a grid of neighbors I want to tune. So grid regular, parameters, KNN model, and I'll say levels or the amount of parameters I want to tune, 5. So if we look at our KNN grid, we can see we have 5 sets of 5 different neighbors that we can, 5 values of neighbors that we can check. And then I'm going to do a tune. So I'm going to do a tune grid, give it a model, give it a model recipe, give it some resamples so we can have some robust estimation of our actual metrics. In this case, it'll be our K volts. Give it our control, which will be equal to our model control. And then we'll also give it our metrics, which will be, what did I call it again? C metrics. Cool. And we're going to tune that model. So let's go back to our actual, I'm going to put this to our, to my other monitor just so I can make sure that it runs. So we can also look at this. So what is sensitivity? Sensitivity is the true positive over the total. So we can look at that true positive, divide by true positive plus false negatives. Oops. We have the specificity, true negatives, divide by true negatives plus the false positives. So right there. So it's this column. There's also a positive predictive value, which is definitely very close to the sensitivity rate, which is the true positive divided by the false positive. And how this differs from the positive, how the positive predictive value or precision basically is different from sensitivity, is precision measures basically how certain we can be that our model is correct, whereas sensitivity basically measures how much of the sample we got correct. So, one goes from the model's perspective and one goes on the data's perspective. But we can look at it in our Yardstick using the Yardstick package. So let's do tune collect metrics. Right now we have basically all of our metrics that we specified. If we do, a ggplot, x equals neighbors, y equals mean, point plus gm line plus facet wrap metric scale equal gm point. So what we can see here is, if we look at it overall, when we increase, if we just look at our accuracy, when we increase our neighbors, our accuracy is increasing. Additionally, our loss is decreasing when we increase our neighbors. Our ROC AOC score is increasing, and also our sensitivity and specificity are increasing. However, with sensitivity, it has a slight downward trajectory, or slight little bottoming. What we can also look at is basically our in sample. So every sample's a metric. So if this is basically the average. We can just look at like the actual frequency of it. So what we can do is we can say select ID and dot metrics, unnest dot metrics. And now what we can start doing is just like plotting that out. So ggplot actually I'll just AS x equals neighbors, y equals dot estimate, gm point plus gm line plus facet wrap dot metric scales is equal to a free y. Right, so now we have a little bit more variance in it. In fact, if we actually do our, our color is equal to ID, we can see all our folds. So I'm going to do theme legend.position equals none. So this kind of shows us why it's good to have every fold. I'm going to do k-folds cross validations so we can see kind of like the variance between each fold or between each partition data set. We can see there's still some stability with, like, say, mean log loss, ROC AOC, and even a little bit of accuracy, but we can see our sensitivity is all over the place. So this is kind of a good for just evaluating, parameter tuning. But one of the things that we should be looking at, right, is just the confusion matrix of it. So how we can do that is if we do our k and k nearest neighbor tune, we can just do collect. We can say collect predictions. And this will give us every fold's predictions with also the class probabilities. So I kind of went over sensitivity and specificity, but let's kind of let's just show the actual confusion matrix. So what I can do is mutate pred equals if else dot pred or prediction is equal to 50% or above. We'll just say it's a yes, else it's a no. And then I'll say mutate pred is equal as dot factor pred. Right, and what we can now do is just use the conf mate, which is confusion matrix, and we can just give it our churn and our pred. Levels are not in the same, so what I can also say is pred equals FCT, reverse pred. So now we have our confusion matrix, right? I'm actually gonna do this and say conf. I'll say C data metric. I'll just C data metric, and then we say C data metrics conf mat churn pred. Pred. So we can see our true positives and our true negatives, our false positives and our false negatives. And really, I would say you shouldn't be too bogged down in the, what is sensitivity, specificity, what's precision recall, what's the false discovery rate. They're all just confusion matrix metrics. So one of the best things I would recommend is just looking at the confusion matrix and figuring out whether it's a good model or not. In this case, if we just looked at our accuracy, right? So C data metric, and we can say, accuracy, give it our churn, and give it our pred. We can see that, wow, we have a 74% accurate model doing basically no tuning, no feature engineering. I just threw it at it, and it's pretty good. 74%, you could probably squeeze another 10% and have a pretty great model. But if we looked at our confusion matrix, we can see that we're not really predicting whether someone will churn or not. In fact, when we make a prediction, we're only right a little bit more than 50% of the time, right? So when we predict yes, 7,500 times it was true, and then 7,000 times it was not actually a churned customer. Which is why if we actually do our sensitivity, we can see our sensitivity score is relatively low. It's 0.5. We really want to maximize our sensitivity score, right? Because our sensitivity score is taking our truths, which is 7520 divided by 7520 plus 7440. Oops. 7520 plus 7440. Right? So out of the total positive classes, how many did we actually correctly guess? We can also measure how confident we can also kind of measure how confident our model is. So the positive predictive value. And that's just doing this. So C data metric. I'll make this a little bit bigger. And what we can do is, come on. Oops. PPV, positive predictive value. So if we give it our churn and then we give it our pred, we can see our positive predictive value is 51, which makes sense because 7520 divided by 7520 plus 747, it should be a little bit higher than 50%. Okay, so that's how our predictive value. So we can say calculate our predictive, our PPV. So these are all metrics of basically like how certain our model can be given an unbalanced data set, or given like if a specific class that we want to specify in. What we can also do is the ROC AOC. So what's good about this ROC AOC is it basically measures to randomly guessing. So if we look at our KNN tune collect metrics, and then we could say filter dot metric is equal to ROC AOC, and then we can say top n mean n equals 1. We can see that our best model has 14 neighbors with an ROC AOC score of 0.79. One way to visualize an ROC AOC score is to show the ROC curve. Because basically when we're trying to evaluate a imbalanced data set, the AOC score is the best way to measure it because it kind of encapsulates and kind of adjusts for the imbalanced data, imbalanced class. So if we look at our KNN tune, collect predictions, and then let's say we do a group by ID. Group by ID, and then what we can do is ROC curve, give it our churn, which is our true value, and just give it our probability of yes. So now we have that, and then what we can do is use auto plot, and it'll auto plot the ROC AOC scores. So the ROC AOC score is basically the comparison between the sensitivity and 1 minus specificity. And the big idea between the ROC curve is that we want our curve to basically touching the left corner. And AOC is just the area under the curve. So basically the more the curve is to the top left, the higher the AOC score. Which is why you need to use the AOC score instead of ROC curve. Because the ROC curve is just a curve, right? It's just a line. There's no like there's not really a measurement of a line. That's why the AOC is basically this summarization of this curve. So that's why we use ROC AOC. There's also other metrics that can kind of substitute to the ROC AOC curve, such as the balanced accuracy. So if we do balanced accuracy, it basically computes the average of sensitivity and specificity, which is kind of like this. However, it does sensitivity and 1 minus specificity. You can also do gain curves, which is which is the same procedure as a ROC curve. But what this is measuring is basically like how much of the cost you can capture given the cost probabilities. So basically it's saying if we say that everyone with the 50% probability of being a yes cost or less is a yes, then we can capture about 75% of the actual points. And then as we keep on increasing, I'm sorry, it's the bottom 50%. Like, so it's saying like from 99 to 0.55 to 0.5, we can capture about 75% of our churn customers. If we keep on increasing this threshold, so right here to basically 0.25 to 100% confident, we can capture about 80%. And you can see that there's a diminishing returns because generally, if we're saying that we're 10% sure, our model's 10% sure that this customer will churn, generally they won't. However, there will be some that slip through the cracks, so you can see this kind of diminishing return. And this is really good for business use cases. So for example, if we are trying to basically spend some money to prevent these customers to churn, so if we have a model that says these guys will churn in the next month, we should send out a coupon or a voucher, worth about like say $10, right? We have some analysts run that. We can't give a $10 coupon to all of our customers because then we'll lose a lot of money. So one way to do it is we'll just give it to the customers who are 90%, who our model is 90% confident or more that they'll churn, because we think that since they're highly likely to churn, we'll give them the coupon first, right? So basically, we're basically trying to find out using a gain curve what are the most vulnerable costs, or what costs are we most sure of that we should start looking at, and how many of them can we actually capture. So gain curves and lift curves, which is kind of this other counterpart, are huge in the business world, and it's something you'll actually probably see. So this is mostly all of the metrics that I would say that you should kind of understand, always be aware about. But what's cool about Yardstick is that there are a lot of metrics. So for example, there's also MCC, Matthews Correlation Coefficient, the J index, F measures, detection prevalence. There's the area under the precision recall curve, ROC curve using a uniform cost distribution. So there's a lot of things. I haven't even gone over mean log loss. But there's a lot of metrics, and I think I'll probably make another video on regression metrics too. But I want to show you one other thing, one other metric that I try to do for all my models after I train it. So, and this is kind of a good post hoc metric to look at. So if we do KN tune, select best, and then our metric is equal to ROC AOC, we see our neighbors is 14. Okay, so in this case, what we're going to do is we're going to create our final model. We'll say, we'll just kind of give it our, what is it? We'll do our finalize model. Was it Mars? What is it? What do you call it again? KNN model, and then KN tune. Select best, KNN. Ooh, what parameters? Oh well, I'll just do this. Sorry, I'm not gonna look up how I do it again. So Canon, so neighbors of 14 has the best ROC AOC curve, ROC AOC score. So what I'm gonna do is I'm gonna go to our model. I'm gonna select this. So 14, so neighbors is equal to 14. I'll say last fit KNN model, and then was it data split? What is it? You must process with. Oh yeah. Sorry, sorry. Geez. Now I'm gonna create a workflow. So final model workflow, add model, KNN model, add a recipe. Was it model rec, and then final res. Give it our final model and our data split. So we did that. So let's say collect metrics and fit to model. So we have our final res. What I'm going to do is collect the collect predictions. Okay. And what I'm going to do is basically mutate. I'm going to select the prediction. So pred class, dot pred, yes, and then churn. So this is what we predicted, and this is the actual results. What I'm also going to do is basically do some mutations. So I'll say dot pred equals 100 times dot pred yes, right? And I'll say select minus dot pred yes. And then what I'm going to do is mutate, and I'll say dot pred is equal to round dot pred divided by 5 times 5. So I'm basically kind of rounding it to the nearest 5. And then finally, what I'm going to do is count dot pred and churn. Then I'm going to say pivot wider names from is equal to churn values from is equal to n. Okay, and then finally, I'm going to say mutate prob is equal to yes divided by yes plus no. And then finally, I'm going to mutate prob is equal to 100 times prob. So what am I doing? What I'm basically trying to measure is, so when we give it a probability of being yes, what is the actual probability of we observing these outcomes? So when we see a probability, if we say that this person will churn 50% of the time, we want to see that these 50% labeled, these costs that we say are 50% of the time will be yes, to actually end up being resulting 50% of the time. So if we do that, so x equals dot pred, y equals prob, plus geom point plus geom smooth. And then what I'm going to do is geom AB line plus chord fixed xlim is equal to c0 100, ylm is equal to c0 100. And what is this? Is basically like kind of like what I think is called like a calibration curve. It's basically saying that if we say, so these are the points where we said, yeah, this will be these customers will churn 50% of the time. 50% of those customers actually churned. Okay, we can say, oh, hey, we're saying that, you know, when we give it like say a 1% of the time, these customers probably actually ended up 2% of the time. So this is kind of a good curve, a good little way to basically evaluate how accurate is your class probabilities when predicting values, and is good for business use cases. So you can kind of actually reasonably assign these probabilities as true probabilities instead of model confidence. So I know we went kind of fast. I was just going over the main metrics of the confusion matrix using classification models. But I think this is basically the main things you really need to go over and really need to know. I would say don't really worry about all the jargon of sensitivity, specificity, true positive rate, false discovery rate, it's positive predictive value. All of that is a function of the 4 main metrics of the confusion matrix. And always look at the confusion matrix think about what you really want to optimize, and then start doing the modeling. So I'll see you guys next week, and tidy on.